Hello, everybody. This is a lecture from the OpenCAPI Big Data Acceleration course. And the lecture will address how to accelerate the pair HMM algorithm used in the GATK haplotype caller on FPGAs. My name is Zaid Lars, and I'm from the Delft University of Technology in the Netherlands. And the lecture is based on a paper by Peltenberg et al. On maximizing systolic array efficiency to accelerate the pair HMM forward algorithm. In this lecture, we will first start with an introduction and define what the pair HMM algorithm does. Then we will discuss systolic arrays and how they are used to accelerate algorithms that calculate matrices. Then we will discuss the architecture of the implementation of the pair HMM algorithm on a systolic array. Then we will discuss how the implementation looks like, and finally we'll end with a discussion of the results of that implementation on the hardware. First of all, our goal of this implementation is to develop fast yet power efficient solutions for whole genome sequencing analysis. The pair HMM algorithm is one of the main bottlenecks in the haplotype caller genomics pipeline. However, we can accelerate the pair HMM algorithm effectively and efficiently using the systolic array structure on FPGAs. The pair HMM algorithm computes the alignment probability of a pair of DNA sequences. In the GATK algorithm, the algorithm starts first with an initialization step, setting a number of different parameters to 0 or to initial value. Then the algorithm iterates on both the DNA sequences that are being aligned. Then 3 matrices are filled out that calculate the probability that a specific character in both sequences is matching or not matching based on a hidden Markov chain model. And finally, the algorithm returns that probability as an output for these 2 sequences. If we look at the way the matrix in the pair HMM algorithm is calculated, we see that there are dependencies in the different entries of the matrix as they are calculated. First of all, we calculate the first top left entry in the matrix. Then we are able to calculate 2 other elements in the matrix, which are needed to calculate the next 3 elements in the matrix. Since each element in the matrix depends on information coming from the top left and top left elements, we can only calculate elements independently that lie as an anti-diagonal in the matrix. This calculation can be mapped on hardware by creating a number of independent processing elements. Each of them calculates an element lying on the anti-diagonal of that matrix. The data in the processing elements of the systolic array is copied to the next element to continue the calculation, and is not written back to the main memory, which saves a lot of overhead of data movement. As we start calculating the matrix using the systolic array structure, a number of overheads are incurred during the calculation. If we consider this to be the matrix that is being calculated, and we have a systolic array that is shorter than the full width of the matrix, the matrix will have to be calculated in multiple passes. In the case in the figure, it will have to be calculated in 3 passes to gradually map or calculate each entry of the matrix in each one of these 3 passes. However, as we do this calculation, a number of times, multiple elements in the systolic array will not be used. And this results in a lot of compute overhead. In this figure, we see a number of overheads. First, we have an overhead that is called the padding overhead, which is, as we calculate the last pass of the matrix, a number of systolic array elements will never be used, resulting in overhead. The second overhead that is induced is when we calculate each one of the passes as we start scanning or calculating the entries of the matrix. A number of systolic array elements will only gradually start to have data to be calculated, resulting in this number of systolic array elements not being used. The same thing happens as we finish the calculation. A number of systolic array elements will finish the calculation and will not be used as the rest of the systolic array elements complete and continue the calculation. There is also an overhead as we move from one pass in the matrix calculation to the next pass, as the systolic array element data has to be scanned in. And this results in yet another overhead as we move from between passes. In order to efficiently utilize this systolic array and reduce the overhead as much as possible, we would like to create a simple performance model to be able to experiment with the various different parameters, efficiency parameters for systolic array utilization. So we start with a couple of assumptions. We assume that the systolic array is fixed with a number of processing elements and specific number of interconnects. And that we assume as well that the desired input for the systolic array is always available. Using these assumptions and using the overhead models that we showed in the previous slide, we can calculate the average utilization of the systolic array. And also we can calculate the average utilization per clock cycle as we calculate in the processing elements of the systolic array each one of those entries of the matrix. In order to decrease the overheads incurred by the systolic array as we calculate the matrix, we start by optimizing our implementation based on the data characteristics. First of all, we notice that our matrix that we need to calculate has one side that is longer than the other. The side that represents the haplotype is usually longer than the side that represents the read. This means if we choose to stream the read bases and the probabilities instead of the haplotype basis, we'll be able to decrease the amount of padding that is needed by the systolic array. The figure here shows how we are able to calculate a 6x6 matrix using a 4-element systolic array. The figure shows that in order to calculate this matrix, we have to run the calculation in 2 passes. The first pass calculates a 4x6 entries of the matrix, and the second pass calculates the final 2 entries of that matrix, which means that 2 systolic array elements will be idle. The figure shows that every clock cycle, we need to pass one piece of data through the systolic array elements. This means that in order to increase the throughput of the systolic array, we need to increase the clock frequency of the processing elements. And in order to increase the processing frequency of the clock frequency of processing elements, we need to use a pipelining structure within the processing elements. However, introducing pipelining in the processing elements increases the complexity, which also probably wastes a little bit of overheads in this pipelining structure. We can solve this problem by introducing batches of pair HMM calculations so that we can calculate multiple matrices together in order to reduce the overhead a little bit. In order to increase the efficiency of the utilization of the systolic array in each batch, we define the concept of batch efficiency. The batch efficiency is calculated as the number of cell updates required in each one of these batches divided by the actual amount of work or the actual amount of number of updates performed in the batch. The number of updates required in each batch is calculated by multiplying the size of each sequence, which defines the size of each matrix to be filled out, and then adding all the matrices to be calculated in each one of these batches together, resulting in the total number of cell updates for the batch. However, the amount of actual work done in each batch scales up with the size of the maximum of the sequences. So in order to reduce the difference between the amount of actual work done in each batch and the amount of required work in each batch, we need to make the size of the sequences in each batch very close to the maximum size of these sequences in the batch. We can achieve this by sorting the sequences before we create the batches, which makes the difference, minimizes the difference between the largest and the smallest sequence in the batch. To see the impact of this sorting approach on the average systolic array utilization, we perform an experiment with the unsorted sequences and the sorted sequences. We see that with the unsorted sequences, we achieve an average systolic array utilization of up to 76%, while for the sorted systolic array utilization can be achieved of up to 90%, which is very close to the ideal systolic array utilization of 91%. In order to validate the results that we have achieved in our work, we run a number of experiments on an accelerator system that uses the Power 8 CPU on a power system with an attached alpha data FPGA that uses a Xilinx FPGA chip. The accelerator is connected to the system using a coherent accelerator processor interface or a CAPI interface that is connected through the IBM Power Service Layer or PSL interface. The architecture of the system looks as follows. We have the Power 8 system on top, connected using the CAPI interface over PCI to the FPGA, which has the PSL interfacing with the CAPI interface to be able to copy data back and forth easily and facilitate data transfer without having to explicitly manage the data copies. Then the interface moves data into the processing elements of the systolic array, where the bases of the reads and the probabilities are gradually streamed into the processing elements. The final result is accumulated in the accumulator from the processing elements of the systolic array and then copied through an output FIFO back to the host processor. First, we run our experiment on 16 processing elements in the systolic array using a synthetic data set. We see that the throughput that we are able to achieve increases gradually with the size of the haplotype. However, it reaches a maximum amount of throughput after a specific size for each haplotype. The maximum amount of throughput that we are able to achieve goes up to about 2.6 giga cell updates per second, which is very close to the maximum theoretical throughputs, achieving up to 99.76% of the theoretical max. When we run the same experiment on a real data set, we see that we are able to achieve up to 4.5 gigaops per second, which is very close to 90% of the theoretical maximum. And this is able to achieve up to 2.5x speed up over the state of the art. Looking at the power utilization of our system, we see that the 16 processing element system, including the interfaces that are implemented for data management and copy, uses up to 11 watts of power. However, the systolic array itself that is implemented by this work specifically consumes only 2.7 watts of power, which is a marginal portion of the power utilized. If we increase the number of processing elements from 16 to 32, this will increase the power of the work of the processing elements themselves from 2.7 to 4.6 watts, keeping the interface power more or less constant, increasing marginally from 11 to 13 watts. In summary, we showed in this work how to implement a new style of systolic array architecture to specifically accelerate the pair HMM's algorithm. We showed that we are able to achieve more than 99% efficiency compared to the maximum possible throughputs for a synthetic benchmark, and we are able to achieve up to 90% efficiency for a real benchmark. Thank you very much for your attention, and hope to see you next time.